Alright, so where we left off, unless a star is big enough, like bigger than our sun, then all these other, after carbon and maybe even a little of oxygen, all these other fusion processes won't happen. But if they do, then these up-down swings will continue until the last fusion process happens. Then um, we reach stage 12 on to 13, and then at 14 in the life cycle process. From stage, 11 to 13, a couple of things are happening, and you can actually see them in both of them in the picture. There's a bright little center spot, bright center spot, bright center spot, bright center spot, and then an expanding, cloudy, gassy, dusty region. So the inner core of carbon, or potentially heavier elements, that can't fuse into anything heavier shrinks because gravity has no competition from outward pressure. As this happens, heats up, as you can see, temperature increases, gets hot. As this happens, heats up but gets dim. Eventually, after stage 12, it gets dim because it's really very tiny, but it can be about Earth size or smaller, maybe slightly bigger. Meanwhile, the core is surrounded by cooler gas and dust that used to be the outer part of the huge red giant, and these are blown outward by the hot inner parts of the star, eventually spreading out to solar system size. Huge. And if you think about it, I'm going to skip back. It's almost like going back to this stage, huh? The very beginning. Actually, it pretty much is. So, yeah, so we're moving down. So you can see a bunch of things happening. Getting hotter, blue hot at some point. Getting smaller because we're moving down 10 solar radii, 1 solar radii, 0.1 solar radii, even smaller. And we're getting dimmer, moving down the y-axis. Stage 13 is known as the white dwarf stage. So the white dwarf is now surrounded by very low density gas and dust, which may even have blown away from other interfering processes. Either way, the white dwarf is left over, and it can be the size of a typical terrestrial planet like Earth, maybe even, like I said, smaller or larger. Very dense and hot. As you can see, the temperature is extremely hot, and even though it's hot, it's pretty dim because it's so small. And depending on the size of the original star, the white dwarf may be composed of carbon or even oxygen or neon for more massive original stars that could possibly fuse those elements together. We'll look at that in a little more detail in a bit. After this, after 13, basically the only thing a white dwarf can do by itself is to cool. Sometimes white dwarfs are near, as you can see here. Here's a Sirius B, a white dwarf. Sometimes white dwarfs are near another star, a companion star, a binary system. If that's the case, we'll talk more about that in a bit. Other things can happen to the white dwarf, but if not, if it's a solo star out alone in the universe, then all it can do is cool off. And so as you can see, it stays about the same size, but it gets even dimmer and cooler, and turns into stage 14, we call a black dwarf, because basically it's so dim that you can't see any light from it. So that's pretty much it for low mass stars. And the thing is, everything I just talked about is pretty much theory. Well, it really is theory because stars are hot, very hot, and far away. Even if they were close, we have one star that's close, our sun. Even though that's one example, that wouldn't be enough to get a good broad idea of what happens in all types of stars. But we can't even probe inside our own star because it's freaking hot, and anything that we send in there is is gone. So we can't really analyze these, so we got to come up with theories based on other processes, nuclear processes that we are aware of. We studied a bunch of that on Earth. But look, the theory in the model matches up extremely well with real-life stars. Here's a globular cluster, M80, and all these stars are represented by dots on the HR diagram. And look at that. You get the main sequence. You got stars who are starting to die, moving up the branch here. Get the horizontal branch, which I didn't really talk about, but it's still a part of it. And we got white dwarfs. So everything is in here, and it's pretty neat. So what else could happen to signal that a star has died, besides turning into a white dwarf and just cooling off over a long, long period of time? Stars can explode. And we got a couple nice pictures of exploded stars here. This one you can actually see something in the center here. So this is what I was talking about. This could represent Sirius B, back in this picture here, Sirius B and its companion star. If the white dwarf is close enough to the main sequence star, and I think I talk about this in the next slide. If it's close enough, then it can actually steal material from the outer parts of the companion star, mostly hydrogen, a bit of helium. Of course, based on orbital mechanics, it won't just fall right into the star. It'll come around with some speed and orbit around, and creates an accretion disk, kind of like a flat pancake disk, that just orbits around the white dwarf, and it'll steal more and more of this material from its companion star. Here's another sort of picture of that. And as it's stealing material, a nova forms. Nova is a very bright increase, not quite an explosion yet per se, but it's a very bright phenomena, increase in brightness. So a nova forms when a white dwarf in a binary system is close enough to steal mass from its companion star. Yeah. And as the accreted matter, mostly hydrogen, because that's mostly what's in the outer layer of the companion star, as it builds up on the surface, the white dwarf, surface of the white dwarf, it heats up. As we've talked about many times before, things heat up as they get more dense, and eventually it reaches a high enough temperature to start fusion again. It's not the same sort of fusion process we saw in a typical star, but it is fusion nonetheless. And hydrogen is fused into helium at a rapid rate. And this process can be very bright, this fusion process, and seen from far away, and we call it a nova. But it's sort of a long process. It happens over a long period of time, although very short on a stellar life cycle, but in terms of an explosion, like what we're going to talk about in a second, a supernova, 50 days is a long time. So it's not really an explosion per se. But, so as a white dwarf continues to steal more and more mass, eventually a limit is reached when about 1.4 solar masses of material has been gathered and accreted around the white dwarf. A limit known as the Chandrasekhar limit is reached, and electrons in this ionized gas, they can't resist gravity. So the star immediately collapses, causing a massive internal rise in temperature. And you see a picture of that here. Type 1, it's called a Type 1 supernova. We're going to talk about Type 2 supernova after. Whoops. Actually, let me get rid of that. So yeah, Type 1 supernova. This causes carbon fusion to begin throughout the white dwarf, which eventually leads to the star exploding. That's called the carbon detonation supernova. The other way that a star can explode is through a collapsing of the iron core. If a star is massive enough, and we saw this picture before, massive enough to fuse all the way to iron, then the star will explode violently. The star's internal structure starts to collapse. As we talked about earlier, through normal fusion processes, iron is the limit. It's the most stable, so it can't go down, can't fuse together into anything heavier. So the star's internal structure starts to collapse from gravity, and hydrostatic equilibrium is not maintained. The core reaches temperatures so high that the photons of light in the core are energetic enough to bombard and break up all remaining nuclei into basic protons, neutrons, and electrons in a process called photodisintegration. What's ironic about this is through all the, actually through all the probably millions of years since big stars like this go through their life cycles pretty quickly, through all the millions of years of fusing all of these elements together, this process of photodisintegration essentially undoes all of that, undoes it all. It just breaks these elements up into literally basic protons, neutrons, and electrons. And the pressure is so high in there that the protons and electrons there are basically squeezed into neutrons, and so all you have in there are neutrons. And this process is called neutronization. Of course, neutrons resist getting closer to each other. They can only get so close before they reach what's called neutron degeneracy. And this creates a pressure which resists the collapse of the star anymore. But like you've seen with the bouncing ball, gravity pulls the bouncing ball down, but once it hits the floor is too dense for the ball to go into it or down any further, and so the ball bounces back, so that some of the energy is stored and released back as the ball goes back up into the air. Same idea. These neutrons are kind of collapsing down, like falling down towards each other, like they're falling towards the floor. And then as they do that, sort of energy is stored, and until they can't get any closer, and then that energy is released, they bounce back out and explode violently. It's known as a Type 2 core collapse supernova, and it's one of the brightest events known in the universe. It's so bright that some of them can be as bright as the entire galaxy. So you can take billions of stars that this star is in, and the brightness from this one explosion can be equal to all of those other stars. That's crazy. Insane. Here's a pretty picture of a supernova remnant. This is actually a Crab Nebula. This star exploded in, what was it, 1054? The year 1054, and the Chinese actually documented and recorded this, and so we're able to know when it exploded. And about 1,000 or so years later, we are seeing this. So it's thought that only hydrogen and helium were these were the only elements in existence after the Big Bang. These two, and that all the other elements up to iron formed from the normal fusion process in stars. As we discussed, iron is kind of like the most stable, so there's a limit there. And so it's interesting that we have all these elements that came from stars, but we still have heavier elements. Where might those have come from? First off, let's kind of review and also mention a new process about how these elements came into existence. Besides the normal fusion process that we saw in the center of stars, you have another process called carbon fusion, where you just take two carbon atoms, fuse them together, and you get magnesium. But there's also this really interesting alpha process, or helium capture process, where you just add a helium atom to an element and it forms a more complex nuclei. So you add a helium to carbon and you get oxygen. You add a helium to silicon and you get sulfur. You add a helium to sulfur, you get argon, etc., all the way up to iron. This stops at iron, as we discussed earlier, because that's the limit. But then beyond iron, we need some other processes that normal fusion can't take care of in the star. There's a couple processes. One of them is known as neutron capture, where neutrons are added to an atom. Of course, that doesn't change what the atom is because you have to add protons to change what the atom is. But you keep adding neutrons, and eventually it'll decay back, and one or two of those may form into a proton and make a new element. So, for example, iron 56, which is that stable element we talked about, can absorb neutrons up to iron 59. So it absorbs a few neutrons, and then it will decay down into cobalt 59, and so on and so on. This can happen for heavier elements, but this is a slow process that happens in heavy stars. And that only happens up to bismuth 209. After that, it just decays back into itself. Bosmith. Let me change that real quick. Done. Alright, so, where did heavier elements than bismuth come from? We're getting really high up in the periodic table now. Most likely they came from the rapid, they formed rapidly during a supernova explosion. So, as I mentioned earlier, like a type 2 supernova, as bright as an entire galaxy. So you know there's a lot of energy there, and enough energy to easily form heavier elements that we actually see here on Earth. And so, it's the circle of life. You start off with gas and dust. Stars form from that. They go through their life cycle. They die and either form, a nice calm planetary nebula like our star would, or heavier stars will supernova, or white dwarfs in binary systems will supernova. Either way, they'll blow up and spread out and form gas and dust, which can then later on be squeezed back together and form stars. And it's a cycle. Pretty cool. Alright, that's it for this unit. Hope you enjoyed it, and talk to you later.